Welcome back. It's been an interesting times, that's to say the least. I hope everyone was rested up during spring break, and I suppose we better go ahead and get started. So, I get to live out my dream of doing lectures in my pajamas and not have to worry about being fired. It's wonderful. Okay, so today we're going to talk a little bit more about adding carbons to aromatic rings, talking about the Friedel-Crafts reaction, and another one called the Vilsmeier-Haack. And then later on, we're going to talk about adding nitrogens to aromatic rings, specifically nitration. So, on Friday, we talked a very good way of adding carbons to aromatic rings was Friedel-Crafts acylation. Where essentially we cut off the hydrogen off the benzene ring, cut off the Cl, and add them together. Which hydrogen is replaced is dependent on what's on the ring already. Such as if we have an ortho-para director, you would get a mixture of two products. Like so. Now, first thing to talk about is ortho-para directors. You do get a mixture of the two, but in almost all of these reactions, the major product is para and the minor product is ortho. One reason to think about it is in terms of sterics. The ortho positions are sterically demanding positions, and these electrophiles are quite bulky, and as such they have a tendency to add para more than ortho. So when it comes to predicting products in this class, the major product when you have an ortho-para director is going to be the para product. There are some exceptions in real life, but those exceptions are few and far between. We also talked about another way of adding carbons to an aromatic ring, and that was via Friedel-Crafts alkylation. And if we use Friedel-Crafts alkylation, we need to use a large excess of benzene because the product that you get is much more reactive than the starting material. And yeah. This has an alkyl group on it. Alkyl groups are activating groups. And so as a result, since this is more reactive than your starting material, you'll get multiple cases of addition reactions to this unless you use an excess of your starting material out competing that. Now with that said, You have to be also cautious with Friedel-Crafts alkylation, because not only do you have to worry about multiple additions, you also have to worry about carbocation rearrangements. Because this molecule right here, being a primary carbon, would form a primary carbocation. Carbocations can rearrange, and this is the electrophile that is added. Friedel-Crafts acylation up above the carbocation electrophile that Friedel-Crafts acylation uses is the acylium cation, which is a resonance stabilized cation. And as a result, this is a major resonance structure, complete octet. No rearrangements take place. Friedel-Crafts alkylation, rearrangements can take place. So that's another advantage to Friedel-Crafts acylation. You don't have to worry about rearrangements, and you also don't have to worry about multiple additions. Because Friedel-Crafts reactions tend to fail on aromatic rings that are strongly deactivated. I.e., if you have an electron, strongly electron withdrawing group on there, doesn't work. Now that doesn't mean it can't work on deactivated rings. Halogens, if you have a halogen on a ring, you can add it on there. And halogens are deactivating groups. So here's a rule of thumb. Friedel-Crafts reactions will generally fail if there is a meta director on the aromatic ring. And this is what the Friedel-Crafts reaction does. It puts a meta director onto an aromatic ring, meaning that multiple additions It is unlikely. Other limitations of Friedel-Crafts chemistry. Aldehydes and carboxylic acids cannot be made directly using this chemistry. What I mean by that? You might be tempted to do something like this. In the case of forming an aldehyde. Or in the case of forming a carboxylic acid. Might be tempted to do something like this. But these reactions do not work. For the same reason we can't go horseback riding on a unicorn. Unicorns don't exist. Formal chloride does not exist at a reasonable temperature. Formal chloride above minus 40 degrees or so, it becomes carbon monoxide and HCl. It's too unstable to be used. This molecule here, I don't even know what its name is. It loses HCl and becomes carbon dioxide. It's also too unstable to be used. With that said, there are other ways around this. Like one way of making carboxylic acid is you can use this chloro ester. It's called this chloro ester right here. And then this can be saponified. to get the carboxylic acid. Or, that's a route to getting carboxylic acid. For the aldehyde, you need to use a reaction called the Vilsmeier-Haack reaction. Which take a benzene ring, and it's a two-step reaction. First step uses phosphorus oxytrichloride and DMF. Second step, add water. And get an aldehyde. DMF is short for dimethyl formamide. Pocal 3 is a Lewis acid that's generally used for this. The mechanism for this reaction follows the same pattern of all the electrophilic aromatic substitution mechanisms. First thing to do is form the electrophile. Phosphorus oxytrichloride, Pocal 3, is a Lewis acid. That Lewis acid reacts with the carbonyl and kicks the chloride off. That chloride adds. And then the nitrogen's lone pair swings down and kicks off the oxygen. And you get this compound right here. It's called the Vilsmeier-Haack reagent. And this is the electrophile. And then, once you have your electrophile, the benzene ring, the pi bond, goes to the electrophile. Forming the sigma intermediate. once you form that sigma intermediate, a base comes to deprotonate it. This is the irreversibles part of this reaction. To restore the aromaticity. And then the nitrogen can swing down, kick the chlorine off. We have this species right here, which is an iminium. Remember, iminiums are unstable to water. This is what you throw water at. And you cut off the double bond to the nitrogen, cut off the two H's off the O. This mechanism is just imine hydrolysis. Imine hydrolysis that's a mechanism from the first unit. Want to see it? Here it is. Otherwise, fast forward. And to finish up the mechanism, you can have water take that proton off. I'm going to have the amine that was kicked off. Take that water off just because the amine is right there. And it's more basic than water. And there's our aldehyde. Okay. So that, the Vilsmeier-Haack reaction is a way of adding aldehydes to benzene rings. And then if you want, you can change that aldehyde into a carboxylic acid by oxidizing it by either chromic acid oxidation or by using the Baeyer-Villiger oxidation. Either one. Okay. Okay. Now, real quick, there are two reducing reactions to know. I meant to cover these earlier, but we just ran out of time. There's the Clemmensen reduction. Which uses zinc mercury amalgam and hydrochloric acid. And the Wolff-Kishner reduction. That uses heat, KOH, and this molecule here, two NH2s bonded to each other. It's called hydrazine. Both reactions reduce ketones and aldehydes to alkanes. Now, this is important. They reduce ketones and aldehydes to alkanes. They do not reduce carboxylic acid derivatives. Okay, now the wording there is very specific. These two reactions reduce ketones and aldehydes to alkanes, but they do not reduce carboxylic acid derivatives. That doesn't mean they do not react with carboxylic derivatives. They do not reduce carboxylic acid derivatives, such as the Wolff-Kishner. So you had something like this. Molecule, it would reduce the ketone down to the alkane. But does not reduce the ester. Instead, the ester is saponified, because in the Wolff-Kishner conditions, there is a lot of strong base and heat, conditions that will cleave, will saponify any ester out there. So you have to be careful on that. Now we're giving you two conditions because one of these is under strongly acidic conditions. One of them is under strongly basic conditions. So if you have a molecule like this that has an acetal on it, if you use the Wolff-Kishner conditions, the acetal is going to stay put. So those are under strongly basic conditions. Acetals are immune to basic conditions. But if you use the Clemenson conditions, acetals under strongly acidic conditions become essentially carbonyls. And these conditions reduce carbonyls. End up with that. So that's the difference between these two systems. We have other ways of reducing carbonyls. But only the Wolff-Kishner or the Clemenson will take a carbonyl all the way down to the alkane. Our other ways of reducing carbonyls, such as sodium borohydride, or the much stronger lithium aluminum hydride, stop at the alcohol. Clemenson and Wolff-Kishner plow right on through and go all the way to the alkane. Now, the mechanism for the Clemenson is actually one of these mechanisms that they're not quite sure of yet. There's a couple of different pathways and no one's 100% sure on that. The mechanism for the Wolff-Kishner reduction, they're pretty sure it is, and at the end of this lecture I will go ahead and write that mechanism up, but I'm never going to require the Wolff-Kishner mechanism on an exam. There are many other things to talk about. So, with that said, what these are particularly good for is, if you remember at the beginning of the lecture, we were talking about adding carbons to benzene rings. And one of the examples I showed was this Friedel-Crafts alkylation. Which ended up giving the major product as the rearranged product. Well, what you can do with these is you can use the Friedel-Crafts acylation to cleanly add a carbonyl on, and it stops here because this molecule is deactivated. It has a meta director on it, and so another carbonyl is not going to be added to it. And then you can add the Clemenson or the Wolff-Kishner, and that reduces off the carbonyl, replaces it with 2 hydrogens, giving you this as the major product. And that's a very common way alkyl groups are actually installed onto aromatic rings. Now, just have enough time to talk about nitration. Nitration is one of the most widely used electrophilic aromatic substitution reactions. What we do is I add a combination of 2 acids, sulfuric acid and nitric acid, to put the nitro group on. Now, for those of you that are in 344, let me caution you. This experiment is the most dangerous experiment you'll probably come across. Mainly because of these 2 acids cause very, very severe burns. And a lot of people, when taking organic chemistry, are wearing gloves, which you should, and then add everything together. But what they forget to do is, after you've worked with sulfuric acid and nitric acid, take your gloves and throw them away and replace them with brand new gloves. Because there are droplets of acid on those gloves, and we get a lot of people burning spots of their face because they reach up and scratch their nose with gloves that have nitric acid or sulfuric acid on them. And yeah, not a good sign. So please be careful. Of course, I'm assuming the labs aren't exactly going to mail out the chemicals for you to use in the bathtub to repeat the experiment. So I don't know what's going on with the labs. So, but just in case they are FedExing stuff for you to use in your kitchen, be especially careful of this reaction right here. Okay, public service announcement over. Moving on. This mechanism. Here's what nitric acid looks like. The Lewis structure anyways. Now, the mechanism for nitration is to form the electrophile. We're going to use sulfuric acid, which is a much stronger acid than nitric acid, to protonate nitric acid. And you protonate the least likely oxygen to be protonated. Why? I don't know. But it turns out, by calculation, this is the oxygen that gets protonated. Not the double bond O, not the O minus, but the OH oxygen. One way to rationalize this is think about you're creating a good leaving group. You're protonating the OH to create a good leaving group. And then you use the O-, swing the electrons down, and kick off that. Giving you this electrophile right here. That's the nitronium. That's a very potent electrophile. And that's the electrophile that's used in EAS reactions. And once you have that, you follow the same EAS pattern where the electrons from the pi bond add to the electrophile. A lot of people, when drawing mechanisms for EAS reactions, draw the electrons from the hydrogen or the hydrogen bond. Don't. It comes from the pi bond. There's a sigma intermediate. And then once you have that sigma intermediate, you deprotonate. And this is an irreversible step to restore the aromatic ring. Okay. So, it's nitration. The nitro group is an incredibly powerful electron withdrawing group. There are a few electron withdrawing groups that are more powerful than that. It's a very strongly deactivating group. Now, let's go through an example of a nitration reaction. Let's nitrate methylbenzene. If we nitrate methylbenzene using our standard conditions, we can install a nitro group on there. The methyl group being an orthopara-director. A mixture of the two. I'm okay with you saying that the major one is the para. Then what you can do with this mixture is nitrate it again. Except now we have a nitro group on this. As a result, the nitration is not as easy to perform because we now have a strongly deactivating group on there. So what we need to do is heat up the system. What heating up the system does is it increases the number of collisions between materials. So now each of these, by heating up the system, is colliding more with nitronium, increasing the likelihood of it reacting. Most of the time that nitronium is just going to bounce off, but every once in a while it will react with it. Now, we have two groups on this ring. When you have a case of multiple substituents on an aromatic ring, you use the directing effect of the most activating group. In this case, the methyl group is more activating than the nitro group. The methyl group is an orthopara-director. The para position is blocked. So we add the nitro group there. In the case of here, the methyl group's still the most activating group, ortho-para-director. It directs it over there, which is the same molecule as that, so don't have to worry about that one. It also directs it to the ortho position, but this one's going to be a pretty minor product compared to this. Now, if you just add heat, sulfuric acid, and nitric acid to this, nothing happens, because now you have two strong deactivating groups on the benzene ring. Very, very strong deactivating groups. So what you would need to do is add in SO3. SO3 is sulfur dioxide. It's sometimes referred to as fuming sulfuric acid. Because when you open up a bottle of this stuff, it fumes. That fume is actually the moisture from the air being sucked right into that bottle. Fuming sulfuric acid is actually quite hygroscopic. What it does is it reacts with water quite violently to make concentrated sulfuric acid. Reason why this is important has to do with how the electrophile is being made. This step right here is reversible. What the SO3 does is it takes water out of the picture, driving the reaction forward. It also increases the concentration of sulfuric acid, also driving the reaction forward. So it's essentially increasing the concentration of the nitronium atom. In a way, it's increasing the lifetime of it, giving it much more chances for even deactivated rings, such as this, to react. And what that can do then, here we have 3 groups on it. The most activating group is the methyl group. So we're going to use that. The only spot left for in the ortho-para position to nitrate is right up here. And this one directs it to here, giving you this as the product. This product has a name. It's called trinitrotoluene, or TNT for short. If you don't know the significance of TNT, then I urge you under the lecture videos by topic to look for the link that says Bowman TNT. I'll probably post another link right below this lecture video as well. Now, what I like about this, other than the fact that it's making TNT, is it shows that you need sometimes different electrophilic aromatic substitution conditions depending on what your starting material is. You might need some rather weak conditions if your material is quite active, but if it's inactive, you need much stronger conditions. Now, I don't expect you to memorize these stronger conditions. Just assume that there's a stronger set of conditions necessary to do the job, and so you might actually have to look those up if you're doing this in real life. The thing is, we're doing this on paper, and so you can assume that sulfuric acid and nitric acid will always work on a ring no matter how deactivated it is. And so if you just had these conditions throughout the entire process, we'd accept it, assuming that each one adds one nitro group. Okay, now you can go ahead and stop the video here. I did promise to draw out the mechanism for the Wolff-Kishner reduction. I have no intention of ever asking a question regarding the mechanism of the Wolff-Kishner reduction. But if you want to see the mechanism, here it is in all of its glory. So, and we will go with this reaction. Which takes heat, KOH, and hydrazine. So the first step is very similar to imine formation. Nitrogen adds, electrons go up. And then protonate. In fact, I think I can squeeze that water here. Okay, now you're in strongly basic conditions. The next step is a slow step, but you use the nitrogen's lone pair to kick off the neutral oxygen. It's not the most favorable process because hydroxide is not the best of leaving groups to be kicked off by a neutral nitrogen. But we are heating this up, providing the energy necessary to go do such a bad step. And hydroxide takes proton off. And we end up getting this intermediate right here, which is called the hydrazone. Now is where it gets weird. Another unfavorable step, we use the base to deprotonate one of those nitrogens. This, of course, has a resonance structure. Which is a carbanion. That carbanion deprotonates water. Next thing happens is base deprotonates the nitrogen again. Again, not the most favorable of reactions because negative nitrogens are typically far more basic than negative oxygens are, hence the heat. But if you look at this, this is actually, if you use these electrons here, they can swing down and they kick off this group. If you follow these electron pushing, you get the source of the ultimate driving force for this reaction. It's the formation of nitrogen gas, which is an incredibly stable molecule. The resulting carbon, right there, has an arrow pointing to it. That means it gets a lone pair and a negative charge. A carbanion that is then protonated by water. Again, I have no intentions whatsoever of asking about this mechanism. That's just there if you are curious. Okay, now, if you have any questions, please post them on Piazza under the follow-up lecture, and I will provide a follow-up lecture to that, answering as many of these questions as I can. And I hope to talk with you on Monday morning using Blackboard Collaborate. So, take care.